Thank you. Okay. Over the past 4 years or so, in my work at Google, I was working at Google Lens. I started realizing that taking a system from a prototype to actually getting production-grade quality, that's a lot of work. It's not just something you do, but you need to do a lot of grind and understand what the problems are. And there's a lot of tools that are related to that. And so me and a bunch of friends from Google decided to go out there and actually help the developers out there and do that. One thing that's maybe common to the theme before is like when we talk about foundational models, one thing that's really nice about foundational models is that they're generic. And in the sense that they're generic, that means they open up to a lot more developers that may not be machine learning experts, but those are people that are maybe coming, those are engineers or developers that are coming from other parts. But now with this new technology, it's made very simple for them to build on top of it. And so they come with high expectations. Like when you think about AI, and especially in the past 2 years since ChatGPT, they expect AI just works, right? So you try out a few queries and it gives you good answers, and then oftentimes they happen to become disappointed as they try to productionize these systems because it's actually a little bit harder than that. So today I want to talk a bit about what it takes to take a system from prototype to production. For these abstractions that are out there, actually, I'm going to talk only from the side of large language models here, and ChatGPT and other like GPT-4 are kind of these foundation models. But in general, I feel like even for vision, this may be applicable in the long run. There's a lot of abstractions today, Llama Index and LangChain and a bunch of vector stores and so on and so forth. That makes it extremely easy today to build applications on top of LLMs. It's literally 5 lines of code here that I have presented here. The second line reads the documents. The third line builds the index, and then you build a query engine, and then the query that will answer your question. So clearly, it's doable for pretty much anyone can build a system like that today. The underlying technology that is used for this is called a RAG. I think by now pretty much a common term in the commodity these days. I just want to spend a few minutes or a few seconds explaining how it works, because that's where some of the issues that we will look at. So initially, when you build a RAG, so you define your corpus of data that you're interested in, that you want your LLM to build hypotheses or answers on. And the way you do it is that you take the corpus. The corpus is then chunked up in smaller chunks, because you cannot fill whole documents into the context of an LLM usually. So you make them smaller, and you project them using an LLM itself, but a little bit smaller one maybe. You project them into a higher dimensional space. Those are the same embeddings that Edwin was just talking about, basically, but now in language space, not in vision space. But so you embed them. And the nice thing of property that these embeddings have is that documents that are semantically close together, they're close in Euclidean space in that semantics, in that higher dimensional vector space. In LLMs, these are usually 1,000-dimensional, sometimes a bit more, sometimes a bit less. Once that's done, you have all of these little locations in the vector space. This is called indexing, that part. At inference time, when you have a user query that asks a question, you do the same thing. You take the query and you embed it in that same space, and you find the closest documents that are there. You retrieve them, and you lump them together in a prompt with an additional context saying, hey, please answer this question, with adding the query. This whole thing is moved into an LLM, and then the LLM, it can be any off-the-shelf LLM, it doesn't be specialized or anything, will then give you the answer in the end. So that sounds pretty easy, right? So there's a lot of things that can go wrong here. So you can start top left. So one thing that's actually really a really big problem, you wouldn't think that 2024 PDF parsing, it's actually something that's not solved yet. So it could be that the numbers, or sometimes actually people, they have text and they put in a white box on top of it because it doesn't want to be shown. As a user, you look at the image, you don't see that text, but the parser sees that text and doesn't really understand. At Google, actually, the way this is solved is that actually the PDF is rendered and passed into a computer vision system to actually parse it out again, because you cannot get it from the structure alone. So that's a problem. Then the embeddings, very likely, maybe they're not multimodal or multilingual, so they may actually not get the nuances of the languages right. The query that is asked may not be like actually, it could be out of the domain of the corpus itself, so, the LLM that wouldn't know anything about it, or the RAG wouldn't know anything about it. In the next step, when the documents are retrieved, the best document that's actually containing the exact answer may not actually be in that context. Sometimes the prompt favors longer answers rather than shorter ones, and there's a bunch of different things that go into the prompt engineering for that then. And lastly, like, it quite often happens that like if you have irrelevant context in your prompt, the LM gets distracted. Like it sees things that are not relevant and starts kind of hallucinating around these kind of things. Oftentimes also you get like generic answers that are kind of like just coming out of the actual the memory that it's in the weights of the LLM itself rather than the actual corpus, the context itself. So what I want to show quickly is just a few examples of how things can go wrong. What I did is a case study. I'm not an oncologist, so I'm not an expert in the field, but actually I learned quite a bit while actually preparing for this. So what I did is I just scraped Wikipedia, 2 pages. One is the list of all cancer types and category cancer, scraped it and put it inside a RAG using the exact 5 lines of code that I was showing earlier. So it's like you can do this like very few lines of code. This is a fairly comprehensive overview of the field. And there's also evaluation sets out there that you can look and get inspirations for questions. I'm going to show you a few examples of what happens with if you just don't spend any time on it and just try that. So this is an example of what is the 5-year survival rate of pancreatic cancer. If you ask it that way, the answer will be the 5-year survival rate for pancreatic cancer is 12% for those who survive 1 year after diagnosis. If you add a question mark at the end, that's the only difference between the 2 queries, you will get the answer. The 5-year survival rate for pancreatic cancer is approximately 12% for those diagnosed. So this is a very different answer. So first of all, like there's a nuanced difference between 12% and approximately 12%. This may not be a big issue in this particular case, but there are other cases where this might be actually a big problem. But the much larger problem is actually the one for those who survive 1 year after diagnosis and those diagnosed, which is actually a different, it's actually a semantically different meaning. One of the biggest problems that we see is anecdotal retrieval, what I call them anecdotal retrieval, because it's the retrieval that retrieves the documents it depends on the embedding itself. And like if you change the prompts, these are 2 semantically equivalent prompts, which cancers are known to have higher risk because of inherited genetics, or which cancer have higher risk because of genetic predisposition, meaning the same thing. But the retrieval stage will retrieve a different set of documents. In this case, the last one is actually different, ovarian cancer versus cervical cancer. Those are kind of close, I guess close by, but still not the same thing. And because of the content of those contain different things, the answer will actually be a different one here. So you'll see, like in one, the ovarian cancer is actually mentioned, and the other one it's not mentioned. And then one of the biggest issues is that this is more not in the retrieval, but in the generative part, is that it's sometimes LLMs are taking it easy with the nuances. So they're kind of getting it right, but maybe not so exactly. And I'm taking the example from before again, the 5 years. So this is the question, and this is the source here, and it says, after diagnosis, 25% of people survive 1 year, and 12% live for 5 years. This is a very different thing than like 12% for those who survive 1 year after diagnosis. It's actually like if you do it right, it's probably like more like 50% of those who survive 1 year. So these are just 3 examples. There are many more that are very complex or very can give a very different meaning, and they're very hard to detect because it's because they sound very similar but may be very different. So how do we fix this? For the machine learning engineers here, I think this is kind of like the standard kind of way of how you do things. But since, as I said earlier, since we're kind of elevating now our are clients to the people that are building on top of foundation models. This is not, there's not the usual thinking that these people are doing, maybe, because they're like used to thinking about, okay, this is a problem. If I think about it hard enough, I can hack it up and it solves my problem. But in this particular case, it's actually a little bit different. So what we actually have to do is a gradient descent of the hyperparameters of the RAG. So kind of depicted here as these rulers here, they're the knobs that you need to turn. And those knobs, they're not differentiable in the same way. I mean, it's, for example, a prompt that you need to figure out, and you need to kind of prompt, like figure these things out, or what's the chunk size, or what is the embedding algorithm that I'm going to be using. And these are the kind of things that you cannot just try out everything, but you have to kind of think about it a little bit. And the way this framework works is that you start with an evaluation set, top left, and then which is usually questions and answers that you want. It's similar like the evaluation sets you have in Vision, where you have like I guess you have your task and you have your ground truth associated with it. Same thing goes here. You have your questions and your answers. And then you run an evaluation where you run all the queries in that evaluation set against your RAG. You generate candidate answers, and in the end, it all comes back together in the metric part, where you compare the reference answer to your candidate answer. You generate a report. You order by your metric. I will talk about the metrics in a second, but you order by the metric, and you look at the wins and losses. And that's when kind of like, for now at least, there's no AI that can solve that problem. You actually have to look at the report, understand what is good, what is bad, why is it bad, and then from that you kind of figure out which knobs you want to turn, and this whole thing goes on. Call it the grind. It's kind of like it's an elaborate task that you need to kind of embrace and do a lot. So let's drill in quickly in the evaluation set. So the evaluation set is like something that defines your product. You should be very opinionated about like your evaluation set. It should kind of span the whole thing that you're interested in. Like in this particular case, it goes from very generic, what is cancer, to maybe very specific, how does HPV cause cancer? And so you want to make sure that like everything is kind of contained in it, because what you're not actually measuring, you have a blind spot. You don't know what's going on there, and you don't know if things go bad there. So the biggest pain point about these evaluation sets is how do you actually get those? There's maybe 2 or 3, I don't know, there's a few ways of getting them, but like the most natural one is like you actually sit down with your with your customers or the person's actually you're building the product for, and ask them what you want to solve with your system. You collect all of these questions. And then you have to do the second tedious step, which is answer all the questions yourself manually. That's a lot of work. So what people do today, they, of course, just use an LLM itself. So you have your corpus of data, and you just throw it at a large language model, and together with the question, please generate question-answer pairs for this set. And so you'll get a very large data set that has question-answers. And it's actually a very good point to start bootstrapping from that list. So you have your list of question answers that are generated from machines, but then you still need to do the work and actually go in and make sure that the answers are correct. But you have a basic set, and so that's kind of a good starting point of getting people kind of into the mode of thinking about what they care about, because they look at the questions and they say, yeah, this is actually not interesting. I'm not interested in that, and these kind of things. Sometimes you also need to explicitly add questions that are spanning multiple documents at the same time. Because like usually like if you ask an LLM, they will just give you a question answer for any single document, but the difficult questions are the ones where the LLM needs to kind of synthesize information from many different pieces. So it's still manual work. What we found to be the easiest way of doing is actually using logs. So once your LLM is in production, I mean, I guess it's a chicken egg kind of problem. How do you go to production when you're not there yet? But I mean, as you get like, when you start going to production, you will get a lot of queries from actual users. And then you can cluster those queries into different domains and then find out what kind of questions are that the people are asking. So that's the eval set. Next step is you run the RAG, you build an evaluation run for that, and so you have your ground truth answers and you have your candidate answers generated from your system. So there's a bunch of different metrics out there that you can use. So this is a selection that we came up with, which we believe is kind of more or less comprehensive. So the first thing is groundedness. So a very important thing is for most of the applications that I've seen so far is that you don't want GPT-4 or any other LLM to answer the question out of memory because you don't know what the source is. Where is it coming from? Where is that information coming from? It's very important that it only uses information that is actually in your corpus. So groundedness measures for a given answer, and the corpus that you give it, it measures how well that answer is actually present in the corpus itself, in the context itself. The next one is comprehensiveness. It measures whether all relevant facts have actually been considered. So the corpus is usually large, has a lot of information. As I said earlier, there's a problem of anecdotal retrieval. So you retrieve a bunch of random documents which contain some information about your topic, but not all of it. And then it gives you an answer which sounds very confidently about, like, this is the answer, but it's missing a lot of information. So you want to be able to measure that. Relevance is the question actually that was asked, is it actually being attempted to be answered? Something can be still 100% grounded. It can be true, but it can just be totally irrelevant to the question. And then there's a bunch of others: answer completeness, harmfulness, and ground truth similarity is maybe one that's quite important because it measures the end-to-end system. So that's when you have your ground truth defined from your evaluation set, it measures how far away is the answer from the actual from the ground truth answer. Measuring that distance is actually non-trivial because it's language, right? So how do you measure the distance between two things that are actually that are semantically the same, but they could be formulated in very different ways? So here's just one example for how groundedness can be computed. So the evaluation query, this example is, who is at risk for head and neck cancer? And the candidate answer is heavy smokers are at risk. The context says laryngeal cancer is a type of head and neck cancer. And then later it says the majority of laryngeal cancer is caused by alcohol or tobacco. So let's just use this part of information. So what's going on here? So the context states that laryngeal cancer is a type of head and neck cancer, and that the main risk factor is tobacco, or one of them. So the answer, heavy smokers are at risk for head and neck cancer, is actually true, even though it's not one-to-one written here. It talks about laryngeal cancer, not head and neck cancer, but that is still kind of consistent with that answer. However, it doesn't mention heavy smokers. It just talks about like use of alcohol and tobacco. So that heavy, even though it kind of like intuitively may be the right thing to think about, but it's not actually grounded in this corpus that we're looking at. So it's very important that these metrics are measuring these nuances. Another example here is ground truth similarity. Now here the ground truth answer, let's say use of tobacco products and drinking too much alcohol can affect the risk of laryngeal cancer. In this case, there's some information that is in the ground truth answer, and some information, like for example alcohol, and some information that is only in the candidate answer. And so again, we're kind of comparing like, what is there and what is not there, and how much information overlap is between the two. In this particular case, will be maybe a third or so. So how do we compute these metrics? From NLP, there has been a field for a long time, even before LLMs. And usually, what people have done is like using syntax-based metrics. Bleu and rouge are examples, or they're like edit distance based, where you basically you have a sentence without understanding the structure or the semantics of the sentence. You just find distances in edit space, like how far away are they from each other. Bleu, for example, is interesting. This metric was built for translation, where they asked 5 different translators to do a translation of a single sentence. So they got 5 different versions, and then they compare the answer to every one of them, and then took the max of the one, or so the one that is kind of closest to them, that will be the answer that they cared about. Something like that. So that Bleu, these are kind of old, out of fashion these days, as you can imagine. Like everybody is doing LLMs today, so you use LLMs to evaluate LLMs, of course. And the prompt is pretty easy. Is candidate similar to reference rate on a scale from 0 to 10? So that's that you can do it pretty easily. Usually you want to be pretty strict about the scoring, like how to explain with examples, like what does it mean to be a 0 or 1 or a 2. But this works actually quite well. The problem with this is it's expensive and it's slow. It's actually, like usually what you do is you even take the answer and you chunk it into facts that are in the answers, and then compare each fact individually. And so you get the cross product of the facts in the answer and in the reference, and so it's getting pretty quickly pretty expensive. So what we need is models that are specialized for that. So what you can do is I could take a BERT model or Roberta or something like that, and just train it on examples. So yeah, and then you get a model which is specialized for this particular task, much smaller because it doesn't need to memorize everything. It just needs to understand language semantics essentially. All right, let's go to the next step. So now we have computed the metrics. We understand what the scores mean. And now comes the part where the human is quite important, but I think this is a step that can be automated fairly soon, hopefully, is where you actually try to cluster your error case. So you look at the examples that are really bad, and you try to figure out what are the common things about them, and you start clustering them. So you could say, for example, the LM only ever uses the first document, or the first chunk. It doesn't ever look at the second one. So that's maybe you want to prompt engineer your way around this, or you find that oftentimes the actual document is not even in the context, and so you start tweaking your ranking algorithm, these kind of things. So this is actually kind of hard work, and you really need to kind of dig in and spend time on this. But this is kind of where you start to generate your facts that will then allow you to tweak your system. So in this particular case, there's 3 examples. You change your prompt, or you change your embedding, or you change your chunk size. But there's a bunch of other parameters, of course, that you might want to change. And then you do the grind. You make your tweak. You very scientifically generate maybe 5 hypotheses about what you believe is the right thing to do. You shouldn't, of course, change too many things at the same time, because then you don't understand what the cause is, and you run a new experiment, and you start from the beginning again. Last step is track and monitor. Once you are in production and you have your system out there, one thing that can always happen is, for example, your embedding provider pushes a new embedding model without you knowing about it, or they have a glitch. Suddenly your index doesn't match your embedding anymore. So you would be serving bad queries without noticing. Or other things can happen, of course. It could also be that the query stream itself is changing, so people are starting to ask new kinds of questions that you're not aware of. So you need to resample your eval set according to your production traffic over time. So there's a drop, you change something, you figured it out, you fix it. And then over time, hopefully, if you do this, things will go better and go up and to the right. Thanks.